Hello guys, so this is part 2 of Thursday lecture. We have finished all the aspect of bipolar junction transistor or BJT transistors. We see how to use them as amplifiers or switches. And we're gonna start now with another type of transistor called the MOSFET transistor. Okay? Or metal oxide semiconductor field effect transistors. Big name. But of course we usually use the abbreviation MOSFET. To know why they call it such with such a name, we need to know or understand how its operation. And to understand its operation, we're gonna do two simple experiment that resembles, in some way how it works. In experiment one, we have a capacitor. We know the capacitor. If you have a capacitor like this with two metal plates, and if you have a voltage, the positive charge will go to some plate and the negative charge will go to the plate near or close to the negative terminal of the battery. We're gonna do the same, but our capacitor now will be one plate is metal and the other plate is not metal. The other plate will be a p-type semiconductor. And we're gonna apply a voltage, let's call it V1. Okay? With that way, the positive charge will be accumulated on the metal plate. And since p-type is connected to the negative terminal, so the holes will be attracted towards the positive terminal away from, the surface of the plate, which is close to the metal positive charge on the other plate. Okay, so that's when the holes move down, it will leave behind negative ion. Remember this from p-n junction, and some minority carriers, which are the electrons. Now, how to control the density of the charge in the p-type semiconductor here? We know that Q, the charge on any capacitor equal to the capacitance of the capacitor multiplied by the voltage across that capacitor. And we know also that C equal to epsilon multiplied by the cross-section area over the distance between the two plates. Here, let's call the distance T. So over T here in that case. So we have two ways to control or to increase or decrease the charge. Number one, if we increase V1 or decrease it, of course. So if we increase it, basically based on that equation here, the charge density will increase as well, or we can say Q will increase. And vice versa. If we decrease V1, the charge density will decrease. Number two, the second parameter is T, the thickness. Although it's not that easy to change it, only during the fabrication of the capacitor. So if T increases based on that equation here, this equation, the capacitance will decrease. So the amount of charge that can be accumulated will decrease as well. So Q will decrease. And vice versa. If we increase T now, we have more capacitance, we can have more charge. Let's do now another experiment. We will call it experiment 2. It is same setup, but now we're gonna add another battery. Let's call it V2. Now we can use V2 to make these static charge. In the beginning here, these charges are not moving, are static. They are static. They are not forming a current. But now when we add V2, and V2 is larger than 0, I, or current, I will flow from A to B. Of course, the convention direction of current is opposite to the electrons. So what would really happen is that the electrons, these electrons here, will move from B to A. How to increase or decrease I? Let's go back to experiment 1. To increase or decrease I, we increase or decrease the charge density. So we play again with V1. So to increase I, so this is number 1. Number 2, if V1 increases, the charge density will increase, so I will increase. And vice versa. If V1 decreases, the charge density decreases, so I will decrease. So what we have done here is that we generate a voltage controlled current, or we can say this is a voltage controlled current source, just like the bipolar junction transistor. How they fabricate it? Now this is, just thought experiment, we can say. In real life, when we fabricate such a device, which is a MOSFET now, we do everything in silicon. So let's see how they do that. So here is how they do it. They have a B-type, which we call B-type substrate or body, which resembles this part here, this part. And then we have a metal, which they call gate. And the insulator in between is the oxide or silicon oxide. This dashed area here, white dashed area. And the two terminals, A and B, are just another, N-type regions, and we will say in a moment, we will explain why they put it as N-type regions inside the B substrate. If we look at the cross-section area like this, so again, here is the metal, here is the B-type region, and here is A and B. The electrons flows from B to A. That's why they call B source and A drain. And here is the fourth terminal, which is the negative terminal of V1, which is the body. They call it body or substrate. So it's a 4-terminal device. A and B, which are source and drain. And the other terminals of V1, this voltage, is gate and bulk. But we usually, deal with only the 3 terminals: gate, source, and drain. Again, the current flows from source to the drain, the electrons current, but the conventional way from drain to source. And we control that current through the gate, the voltage on the gate. Let's have some notes here. Let's write some notes here. So some notes. Number 1, the gate when they first introduced such a transistor, it was really made of metal. But nowadays, it's easier for them, and it's advantageous to fabricate it from another material called polysilicon. It's made of a material called polysilicon. It is still conductor, so it can be used. What we need is a conductor. So nowadays they fabricate it out of polysilicon, not metal. Number two, the MOSFET has 4 terminals. The source, the drain, the gate, and the bulk, or the substrate, the B-type substrate. But most of the time, we just connect the bulk to source, usually connected, and then we just use drain, source, and gate, and that's it. Number 3, it's a symmetric structure. If you look, there is no change. If you look from right, it's just like looking from left. I mean, the drain can be used as a source, and source can be used as a drain. I mean, if you make the battery in the opposite way here, the current will flow, in the other direction with exactly the same value, as long as Vg is constant or V1 is constant. So it's a symmetric structure. Remember, in NPN transistors or PNP transistors, the emitter usually heavily doped than the collector, so it's not asymmetric. Although this is N and this is also N, but this is heavily doped, so it's N plus, not just N. But here, no. Another observation also is about the dimensions. So let's look at the dimensions here. So first, this is called the channel. The distance between the source and drain is called the channel. So L, this L here, this dimension is called the channel length, or the distance between the source and drain. Distance from source to drain. The width is the width of the transistor. So this is the width here. Or the width of the channel, or the other direction. So channel width. Another parameter also is, as you see here, it's very small. The thickness of the oxide or the insulator, the distance between the two plates, T. We call it T oxide. So T ox is the oxide thickness or the insulator thickness. Number 5, the last remark or note here is a symbol. So of course, in a circuit, we are not using, drawing the whole structure. We have also a symbol, and the symbol is very simple to to remember even, or to construct. So let's do it here. So you have a gate. This is the terminal of the gate. Then you have the gate itself. This is the gate. Then you have insulator, then the p-type. So you have here the gate terminal, the gate itself, insulator. Then you have the p-type. Then you have the source region and the drain region. That's it. Okay. And to differentiate between source and drain, although it doesn't matter, they usually put an arrow like this at the source. So we have the gate terminal again, gate terminal, the gate itself, insulator, then the p-type substrate, then the source, then the drain. And they put at the source an arrow like this. This is the symbol. Good. Now let's see the operation. So the thought experiment that we did, experiment 1 and experiment 2, is a very good approximation for the real operation. But the real operation is a little bit different, and we see how much it's not that different, but there is some differences. Okay, so let's explain now the operation on, the structure itself. So the operation here, let's write this operation. Okay. So basically, first we're gonna assume that there is no voltage at the source and the drain, or they are both zero. So we connect the source to ground. We connect the drain also to ground. And you put a battery VG here at the gate. So, number one, when VG is just equal to 0, this will be just a p-type and that's it. So, no negative charges is seen between the source and the drain. Let's have a copy and paste. Number two, we're gonna increase VG a little bit. In the beginning, at very low values of VG, it's positive. I mean, we increased it, but with very low values. So what will happen first is that the holes will go away from the channel or the region between the source and the drain, and only negative ions will be there. At some point, let's now draw another. Or at some value of VG, which we call V threshold, another interesting phenomenon happens. So number 3, when VG approaches a value called V threshold. Some electrons from the source and the drain regions, and remember they are N-type material, they have a majority of electrons, will flow to this area here. So electrons from the source region and the drain region, you know, will flow to the channel. Because of course they are attracted to the positive voltage of Vg. And this is important, and this is why we did the source and the drain region with N-type materials, because it's not enough our minority carriers, which is electrons in the p-type region. And at that point and forward, I mean for any value larger than even V threshold, this region here will be N-type region. So this channel, we can say, is actually N-type. So the electrons can just flow there, you know, easily with a good current, good amount of current. And this is called the strong inversion because it was a p-type material and now it become an N-type, or part of it become N-type. That's why they call it a strong inversion. So here, let's be more formal now. Here Vg is larger than 0, yes, but less than V threshold. So just negative ions between the drain and the source. Good. Since this is N-type region or N-type channel, we call this NMOS. So at number 3, so let's write it here. Since the channel is N-type, we call that NMOS transistor. Okay. Now we're gonna fix Vg. So let's assume number 4 here. Vg is larger than or equal to V threshold, but fixed. And we're gonna apply now a voltage between the source and the drain. So VDS now is larger than 0. Remember in the beginning here, VD was 0 and VS was 0. Now we're gonna apply a voltage. We're gonna keep V source at 0, but VD will be larger than 0. So we have a voltage difference, remember, between A and B in the first experiment or the second experiment. Now there will be a current flow. So under that condition, that would lead to a current will flow from the drain to the source. And this current will be controlled by the voltage on Vg. So this current will be, or can be controlled, it's both the same, can be controlled through the voltage Vg. And all the time we relate the voltages to the source. So usually put the source at a lower voltage and relate everything to the source. So from now on, this is not just Vg, we will call it VGS, 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 again VGS, and VGS. And we did this already here with VDS. So this is also VGS. Okay. And one last thing here is that number 5, again, this is just a conclusion. At VGS less than V threshold, we have no channel. So even if VDS is larger than 0, there will be no current. So no current, whatever the value of VDS. As long as VGS is larger than or equal to V threshold, there will be a current, if there is a voltage. Okay, guys. So in the next lecture, we're gonna, take these observations and try to deduce the characteristics of that device. I mean, ID versus VGS and ID versus VDS. Just like what we did with IC versus VBE and IC versus VCE in BHT transistors. Okay, guys, thank you very much and have a good day. Bye-bye.